Greetings, welcome to this new video about Norton's theorem. In this video, I will show you how to use Norton's theorem with an easy to follow example. By watching carefully, you will learn how to apply Norton's theorem to solve practical problems. Let's get started with solve the problem number 5. Let's consider this network consisting of 3 resistors labeled R1 through R3 as well as 2 independent current sources IA and IB and 1 independent voltage source Vs. The question now is to find the Norton's equivalent with respect to terminals A and B. Let's move on to the solution. By applying the Norton's theorem between terminals A and B, we can replace this circuit with a current source in parallel with the resistor, which will be denoted as IN and RN. I will start first with the determination of the Norton's resistance RN. This step can be done by removing all independent sources in the circuit, which means the voltage source Vs will be replaced by a short circuit and the current sources IA and IB will be replaced by an open circuit. The Norton's resistance represents the equivalent resistance between terminals A and B. That means Rn is equal to the series combination of R1 and R2 connected in parallel with the R3. Therefore, Rn can be calculated using the following formula: R3 times R1 plus R2 over R1 plus R2 plus R3. And if we replace the resistors with their numerical values, we obtain Rn is equal to 4 ohms. After finishing the determination of the Norton's resistance, we proceed to calculate the Norton's current IN. The Norton's current is basically the short circuit current calculated between terminals A and B. The resistance R3 is short circuited, meaning no current flows through the resistor R3. To find the short circuit current ISC, I will apply Kirchhoff's laws. But first, I will consider I1 is the current through the resistor R1 and I2 is the current through the resistor R2. By applying Kirchhoff's current law at node 1, we can write IA minus I1 minus I2 is equal to 0. That means 1 minus I1 minus I2 is equal to 0. And now by applying Kirchhoff's current law at node 2, we can write I2 minus IB minus ISC is equal to 0. And if we replace IB with its numerical value, we obtain I2 minus 3 minus ISC is equal to 0. Now by applying Kirchhoff's voltage law in loop 1, we can write negative R1 times I1 minus Vs plus R2 times I2 is equal to 0. And if we replace the resistors and the voltage with their numerical values, we obtain negative 6 times I1 minus 14 plus 14 times I2 is equal to 0. Now by performing 3 minus 6 times 1, we derive one equation in terms of I2. From here we can calculate I2, which is given by 20 over 20, we get 1 amp. And from 2, we can write ISC is equal to I2 minus 3. And if we replace I2 with its numerical values, we obtain ISC is equal to negative 2 amps. And we know that IN is the short circuit current ISC calculated between terminals A and B. That means IN is equal to -2 amps. After completing the calculations, I perform a simulation using SPICE to verify our results. Now let's proceed to the SPICE environment. Here is our networks drawn in SPICE simulator. This is the original circuit and this is the Norton's equivalent circuit. I connected a load resistors between terminals A and B to both the original circuit and the Norton's equivalent circuit, and then I will simulate their behaviors. Let's move on to analysis. DC analysis, calculate nodal voltages. We can see here that the voltage across the load resistor is equal to -267 volt, and here is equal to -2.67 volt in the original circuit, and the current flow through the resistor the load resistor, is equal to -1.33 amps, and here is equal to -1.33 amps. Through simulation, we can observe that the two circuits demonstrate identical behavior when we connect a load between terminals A and B. This outcome confirms the validation of our calculations. Alright, thank you for watching this video. If you have any question, do not hesitate to contact me by email or leave a comment under this video and I will answer you as soon as possible. If you like this video, don't forget to subscribe and share. See you next time in another video about Norton's theorem. Take care and bye bye.